Okay, hello everyone. Sorry for being late. That's actually, I think that's the first time when I was late to the stream, but that was for, I think, a good reason. So yeah, I hope that we'll have a nice stream today where I will show you a bunch of cool stuff about our latest model. So before we start, just let me know in the chat if you hear me. And if so, we will start. So I'm just waiting for the confirmation that the sound is okay and we should be good to go. Can hear. Awesome. Okay, guys. Thank you very much for the patience. Like I wrote in the chat, I was running experiments pretty much to the right to the finish line, and that's the reason why I was late today. But I thought that there is one important thing about the model that I should be able to show you, and I really wanted to be able to do that. Okay, cool. So let's start. Let me just share the screen. Awesome. Okay, cool. So here's the repo of our model that we released pretty much a week ago. I remember because we were like, that was super, crunch time. But we managed to do that. And this is a fully open source object detection model that we released under Apache 2 license. The code is under Apache 2. The model is under Apache 2. So the checkpoints, everything is fully open source. That means that, yeah, you should be able to use our model in enterprise projects if you want to, without any sweat. Yeah, that was a dream of our founder. That was a dream of myself to release something like this. That was a dream of a lot of people within Roboflow who actually built that, like Peter and Isaac. So I'm super happy. So today I will tell you a little bit more about the model, why you would use the model. Of course, I will try to answer all of your questions from the chat, but maybe first a little bit of introduction, and we should, and I will just take questions after that. Cool. So RF-DETR is a, like I said, fully open source model that scores over 60 MAP on COCO dataset while still maintaining real time. I think that according to papers with code, real time is like 20 or 25 frames per second. Don't quote me on that. I'm not exactly sure about that particular number, but we definitely qualify under papers with code criteria to be real time and cross 60 MAP on COCO dataset. But that's not the most important part about the model, because what's actually the key, kind of like the most important thing about the model, is that it is really good at fine tuning. And that was the thing that I really wanted to prepare before the stream, because I have like a, example showcasing that. Some of you probably, if you were following Twitter or LinkedIn, many people started to play with RF-DETR and showcased exactly what I want to showcase. But I have my own example, so I'm super happy about it. So let's take a look at the numbers. So, like I said, we are very good at COCO. But when you think about like benchmarks on MS COCO, probably the last 2 or 3 years, everybody is just slightly above any other models on that leaderboard. So it's not necessarily a big achievement. I mean, it is a big achievement to be SOTA on COCO, but nobody is really like kind of like blown away by that fact. The important thing is that a lot of people don't use COCO. For those of you who don't know, COCO is like those like 80 classes that you always see, like person, car, and I don't know, apple and banana and so on. Many of you probably right now actually fine-tune models on your own custom data sets. You know, Roboflow is the platform where you can do that. And this is where RF-DETR shines, when you need to fine-tune it. And before we dive into the kind of like the numbers, I want to show you an example. So just before the stream, like literally just before the stream, I tweeted this, and this is the example that I want to show you. So over here is an example of an use case where you fine-tune a model on your custom object detection dataset, and in our case, that dataset is a license plate detection dataset. And before we watch the video, which you know is also really cool, I think that we will take a look at the at this chart. So this chart shows you how fast models converge. So pretty much that means that this chart shows you how many epochs it takes for the model to get to a meaningful result. We are using mean average precision to measure that. If you don't know what is mean average precision, I'm not sure if I wrote that blog post or was that somebody else from Roboflow. Yeah, that was Jacob. So you can take a look at what mean average precision is, but pretty much is the standard metric of measuring how well the model is doing. And what is very important about RF-DETR, we are the orange chart. So you can see that pretty much from the first epoch of training, the model is already really good. And it takes a comparable model like YOLO11M, a considerable amount of time, around 30 epochs to get to the same level that you get after 10 epochs with RF-DETR, and this is where the model shines. So you can train your model shorter, and that's a big difference. Yeah. So let's take a look at the results. So here's a video where I compare a RF-DETR model that I got after 10 epochs with YOLO11M model that I got after 30 epochs. So I trained pretty much 3 times as long to train a model that I'm not sure if it's better, to be honest. It's very close. I think that we have cleaner detections. We can detect some objects that YOLO can't. But even if we don't think about which of those models is actually better, although, like I said, I am pretty sure that, yeah, at least on this example, we are doing better. Think about it. We trained for only 10 epochs versus 30 epochs with YOLO11M. And now, why am I using YOLO11M as a comparison? Because if we go to our repo and we take a look at the amount of parameters that we have in the B version, which is the basic version, it's fairly close. Yeah, so it's a model that is pretty much have the same speed, pretty much have the same accuracy, but because the RF-DETR is optimized for trainability, it takes significantly less time to train that model to the same standard. Yeah, so this is the important message. Now, we, along with the RF-DETR, we released another project, which is RF100-VL. We released the paper, and maybe the paper for RF-DETR will come. I'm not sure, because Peter and Isaac, who kind of like worked really hard on that specific model, they are pretty tired, because like I said, it was a crunch. Well, 50% more params. Somebody is saying that it's 50% more params. Sure, but if you take a look at the table and how larger models look like, so we only took this one because it's the closest. The next one is already larger, yeah. So there's that, and also parameters count doesn't really matter that much, because like you saw, Chris, like you saw, the speed of that model is pretty much the same. So a lot of people use parameters as the kind of like, how to say that, a way to represent how slow or big the model is. But in reality, parameters are not the same, pretty much. That's what I'm saying. There are certain operations that you can perform where you can have less parameters, but they will take more time to execute. So it can kind of like translate into amount of memory that you need to have to run the model. That's right. But when it comes to speed, that's not necessarily a good measure. So if you care about the memory, then sure. If you care about the speed, they are pretty much comparable. Cool. So, and there is also maybe small important fact, but I think that's a good point to say that when we talk about the speed. YOLO model need to have another component on top of the model called non-max suppression. I talk about it a lot during our streams. Oh, it's not the one. I talk about it a lot during our streams. So if you don't know what is non-max suppression, take a look at this article that I'm just that we just have on the screen. I can send you the link. And by the way, we have like 100+ people on the stream. Leave a star under RF-DETR repo in the meantime. That would mean a lot to me, you know. I'm kind of like leading open source stuff at Roboflow, so any stars for me just move me a little bit closer to the final goal. But back to the non-max suppression and how that influenced the speed. So YOLO models typically, when you look at their benchmark, they report the speed without NMS, but they report the accuracy with NMS. So NMS is something that you run on top of the model. That will be, that will pretty much do what you see here. So very, very often, YOLO model will produce double bounding boxes for specific detections, and you use NMS to reduce that. It's pretty much a mathematical operation where you pretty much compare how big is the overlap between different bounding boxes. And if you know anything about computer science, of course, if you have more bounding boxes and you need to compare each with each, it's not a linear increase. So very often when you have a scene where you have a lot of detections. The NMS can take a lot, it's still milliseconds, but in context of real-time object detection, every millisecond matter. That operation takes a little bit of time. And this is an operation that you need to run for pretty much any object detector that is convolutional neural network based. But RF-DETR is actually not, in the name, is a detection transformer because it's Roboflow detection transformer. So transformers don't need non-max suppression. In practice, very often you need to do that, and I know that you don't need to believe me because I work at Roboflow and I kind of like I said, I build that stuff, but it's the first detection transformer that, in my opinion, really don't need NMS. Because before that, it was very often you got non-optimal results, but with RF-DETR, I really don't use NMS in any of my examples. All you need to have is set a pretty hefty confidence threshold, like 50%, and that's it. Yeah. So what I'm saying is you can save that time that you usually would spend on running NMS to actually run faster and process videos faster. So there's that. But as I show you this example of how fast we converge compared to models like YOLO, we actually tried to measure that. So we released this paper. This paper is called Roboflow 100-VL because we released Roboflow 100 some time ago, but that was not a vision language benchmark. But this time it's a vision language benchmark. So we have detections, but we also have questions and answers. We have some OCR benchmarks. So anything that you would need to benchmark vision language models. But we took the component that benchmarks detection models, and we benchmarked several models that right now are very popular to measure pretty much how well the model fine-tunes. So what we did is we took our pre-trained checkpoint on COCO dataset and we fine-tuned model for each of the datasets in this RF100 dataset. So we pretty much trained 100 models of RF-DETR, 100 models of YOLO 11, 100 models of YOLO V8, and so on. And we compared how good is the fine-tuned model. We ran every model for 100 epoch, and we took a look. And those are the results. So on average, over here, yeah? So on average, when you train a model RF-DETR on those datasets, you get around MAP of around 86. And on average, you get around 84, 85, 83, depending on the size of the model from those other models. So it's not only on the license plate detection dataset where we see that we can converge faster and we can actually get better results because, we have this, capability to just go slightly further because we converge faster. It's actually something that we measured on 100 datasets, and it's in most cases true. What is cool about RF100-VL benchmark is that we actually split those datasets even more. So we split those datasets into several cohorts, 7, if I recall correctly, and plus 1. That is the average. So this chart and this chart is pretty much the same. So you can see that pretty much on any type like fauna, flora, industrial, medical, aerial, sports, and others, we score higher than YOLO models. There is only one type of the data set where we score slightly lower, and this is the document, and we actually don't know why is that, so we need to dive a little bit deeper. But there is like one data set that tanked our performance, and we were significantly worse than YOLO models on that one data set, and that was enough to kind of like tank the whole average of those benchmarks. But in general, it performs really well, I think. Okay, so there's that. Now, what I would like to do is I would like to show you how to run the model and how to train the model. And now, importantly, you can run the model in several ways. So you can run the model using RF-DETR SDK that we built over here. That code, like I said, is Apache tool. And we have checkpoints pre-trained on COCO dataset that are also under Apache license from this code base. I mean, I didn't because I was doing other stuff, but other people in Roboflow, namely Medvey and Pavel, I guess, spent a little bit of time probably few days. So there's that, to integrate RF-DETR into our Inference package. So this package is pretty much where you can run any model that is on Roboflow platform, plus foundational models, a bunch of different things that you can do. Yesterday they released release number 0440. This is probably a patch to that. Yeah, where they added RF-DETR as one of the supported models. So like I said, you can run the model from our SDK, or you can run the model from the inference here. And also, you can train the model from our SDK, or you can train the model in our platform. And I will show you how to trigger that in just a second. And I'm not sure when, but Hugging Face Transformers will also support RF-DETR. There's already pre-advanced PR over there from one of the people from the community. I don't recall the nickname right now, but if you are on the stream, thank you very much for the work. Okay, cool. So there is a question: can the model be exported into CoreML format? CoreML is iOS, I believe, format that you would run on the phone. So right now we only support export to ONNX because we pretty much started from the scratch. We didn't have anything in that code base. So, you know, there are other frameworks that pretty much copy paste the code from other stuff, but we wanted that to be fully open source. We wanted that to be released under Apache. So we couldn't just copy paste from other repositories and just slap pretty restrictive license on top of the code base. We want to write everything from scratch. So right now we only support the export to ONNX format, and we'll pretty much roll out support for other formats along the way. Yeah. So right now there is CoreML. I know there is already a conversation about exporting that, or there was, and there is already no conversation about it. There was definitely a conversation about it. Regardless, I won't be able probably to find that conversation, but we are talking about exports to other formats. So you can, TensorFlow Lite, sorry. Yeah. So we will probably add export to other formats with time, but for now it's only ONNX. But you probably can convert ONNX to CoreML. How does RF-DETR compare to RT-DETR? So RT-DETR is probably the original, the OG of real-time object detection with transformers. RF-DETR is is better, both when it comes to speed during the inference, I think, but definitely when it comes to like training and fine tuning. It's just significantly easier to fine tune than RT-DETR. So unless you use the pre-trained RT-DETR when you use COCO classes, then maybe, but if you fine tune, I think there is like no comparison. Would it be possible to have a smaller version? I know that the team, so I will just answer some of the questions that I see on the chat before we dive into the Colab session. People would like to have a 10 to 12 million parameters version. I know that our team kind of like experimented with distillation of knowledge from the larger model into smaller models. We just didn't have time to make it before the release. So I'm not saying no. If what I would probably say is that if there will be an interest from the community around the model, and right now there is, then everything is possible. I know that we experimented with that, like I said, so it's not completely off the table. Have we tested that with different quantizations? I think that the only floating point 16 was the only one. We didn't experiment with the other ones. People also asked in the GitHub issues about quantization. So I think that will come at some point. Can RF-DETR support YOLO format? That's another question that a lot of people ask us, because right now you can only fine tune from COCO datasets. But, you know, what you can always do is just upload your dataset to Roboflow and convert it to COCO. You can also use Supervision or other open source package. Here, you don't need to upload anywhere. You just run it locally and you can convert your datasets from YOLO to COCO. So I think at some point we'll support different formats like YOLO, because, you know, big part of the community is using YOLO formats. But realistically speaking, we have so many other things to fix and improve in the repository. I think that we will not do that like immediately, maybe at some point. How difficult would it be to convert a project using Ultralytics import YOLO to this model? I mean, if you train the model, it will be extremely easy. Like, I think it will be import that you need to import from our SDK versus import YOLO from Ultralytics. And then you have model initialization, and that's it. The rest of the code probably can stay the same. So yeah, we use PyTorch as the kind of like the workhorse behind the model. They also use the PyTorch as the workhorse behind the model. So I think you can certainly migrate if you would like to. And like I said, you would get Apache 2 license. Could you let us know whether RF-DETR can be also modified the way YOLO versions could be? I mean, YOLO versions have been completely open. How about this one? I'm not sure if I understand the questions. That question. So, Matthew B, if you can just, you know, give me a little bit of background in that questions, I would definitely appreciate. These transformer models can't run in CPU in real time, right? Yeah, I mean, we can run pretty fast on CPU. I mean, I run it on Mac, and I have pretty good Mac, and it is pretty fast CPU. So in my case, I can run pretty fast on like 10 FPS, maybe even. I'm not sure, but on the Intel, we're probably a little bit slower. How many examples do you need for fine-tuning? I will train model on that stream on like 300 examples. I trained that model to detect license plates on like 10,000 examples. But I think if you have several hundreds, you should be fine. Okay, cool. So now I think let's go into the notebook and let me show you how to fine-tune the model. So we will use the open source SDK to do that. But maybe before we will jump into the open source SDK, let me just tell you that we also support in-platform training for that model. So let me just show you how to trigger that, but I will primarily show you in the Colab how to do it. Where is my favorite data set to detect football players? Okay, here it is. Okay, so if you would like to train the platform, then what you need to do is you need to click here, train the model, custom training, create a new data set version. So I will just do one change. I will scale down my images. I will be using kind of like stretch tool. What else should I do? Auto orient probably, and that's it. I don't need anything else. Continue. So if we talk about training in platform where you don't need to run any code on your own, you need to have a data set, you need to create a version, you have the version, you click custom train, and here you get to choose the options that we support. You choose RF-DETR, still experimental, but it is what it is. You choose the base, which, like I said, we have two sizes. We have, or I didn't say that. Maybe I will just quick segue. We have two versions. We have the base version that has 29 million parameters, and we have the large version that has 128 million parameters. So when you need to have a very accurate model and the speed is less important, you would use large. If you need more of a speed than accuracy, then you would use base. Yeah, so base is 28 million, large is 128 million. So back to the UI. Here we only support base for now because it all happens pretty much this week. And then you choose a checkpoint and you can start the training. Now, important thing is that we have two sets of checkpoints. We have a COCO checkpoints. Those are, like I said, Apache 2 license. You can pull them from our servers. You can run them in our SDK and everywhere. And there is also a second set of checkpoints that is fine-tuned on COCO and Objects 365 dataset. So we pulled a lot more data into training those checkpoints so that those pre-trained checkpoints are just stronger. And those checkpoints are not available like openly. You can only get them in platform. So here's the only place where you can use them. We actually don't release them to kind of like run the inference on its own. We only use them as the baseline for fine tuning. So in the platform, you get this kind of like edge because you get stronger baseline model that you can use for training. So you choose that checkpoint, you press start, yeah, and the model is training. So that's how you do it in the UI. Now, let me show you how you do it in the Colab. So at the top of the RF-DETR repository, we have the link to our Colab. I will also send that link in the chat. So if any of you would like to follow along, let's call it this way, then feel free to do that. As for myself, I'll just follow that link. Now, I will use this notebook, but I will also kind of like use latest features that are not yet released because, like I said, everything moves really fast. So here's the notebook. The first cell I'm running as I'm just providing environment variables to the tokens that I have, because we will need Roboflow API key to pull the data set from Roboflow universe. So there's that. I will also maybe, okay, you know what? We'll just small change. Sorry, guys. What I want to do is have access to larger GPU, and I have that access on this GitHub, Google account. So sorry for that. I need to switch. Okay, so once again, I'm opening that Colab that I mentioned. I'm providing those API keys that we spoke about. So we run the Colab. I should have access to NVIDIA A100. That's why exactly. Okay, so I wanted to have access to NVIDIA A100, but you can train the model on T4. It's just Stream is very concise when it comes to time. So I just wanted to have larger GPU. Okay, cool. So now, like I said, I will not run the model like this because I would like to have access to my latest features that we not yet released. So let me just grab the command to install locally. Okay, cool. I have it. Okay, so typically I recommend installing from our pip package. We have a Python package that you can just use. So here is our Python package that we released, and generally speaking, I recommend you to use that package, but we have certain features that we are not released, but I would really like to use them because I want to show you that we have them, that I will install from source this time. So I'm installing from source from a specific branch. That is mine branch. And what I did in that branch, I enabled TensorBoard integration. So we will be able to hopefully in kind of like real time see the performance of the model in the TensorBoard. Cool. So the installation will probably take a few seconds to complete. It's not like the largest package, and most of the heavy dependencies are already pre-installed in the Google Colab, like PyTorch. So you should be ready to go in just a few seconds. Yeah, thank you very much for sending all of those very important links. Somebody from Roboflow is helping me out. I have no idea who that is, but whoever that is, I'm highly appreciated. So, okay, we are pretty much wrapping up the install, and we should be good to go in just a few more seconds. Yeah, in the meantime, I can show you that our training in Roboflow platform has started. So, yeah, you can see side by side that you can train the model two ways. You can train it in Colab and you can train it in platform. Yeah, I didn't plan for that, but it's a pretty good idea to show it side by side. Okay, cool. So the first thing before we jump into the training, I will show you the inference. So the inference is really simple. You just import the class that you would like to associated with the version of the model that you would like to use. So like I said, we have large and we have base. So I'm just importing RF-DETR base from our SDK. In our README, you can see how to import the large one. So, it's James in the chat. Thank you very much, James. Thank you very much. That's very helpful. Okay, so in our README of the SDK, you can see how to import the large one. I'm using the smaller one, but that doesn't matter. Pretty much this is the initialization of the model. Maybe I will just increase the font a little bit. So here is the initialization of the model, and here is the inference. So as you can see, you pretty much need 2 lines of code to run the model and infer with it. We are still waiting for ReID. I can promise you guys that's just a side note, because we will release package this year that will handle ReID. So just stay tuned. I will not only give you the tutorial, I will give you the whole package to do it. What the model is doing is it's returning detections. So this is the class that it's coming from supervision package that I described before. And because you get the detections out of the box, you can use all other tools from supervision package, like annotators. Yeah. And here is the result of our inference. Like I said, base model, yeah, that's it. Now, if we would like to run the large one, all you need to do is change that base into large. I can't type and talk. Run it over here. So you just import like this, you swap that, you run it, and the inference will happen. You just need to pull the model, and that model with over 100 million parameters is pretty large. So it will take a little bit of time to pull and load, but yeah, you know, if we are here, I can just as well show you how to run the inference. Okay, I was talking for 50 minutes, so let me just drink a sip of coffee while we wait for the model to download. And we should be good to go in just a second. Awkward silence. I could tell you a joke, but I will just probably not do that. I will better show you the stats from the training happening in the platform. Where to deploy the model the best way? Probably through Inference Package, but I will maybe show you how to do that in just you know, in the second part of the stream. But I just don't want to promise because we are already 54 minutes in, so there's that. And here's the prediction from the large model. So for example, you could saw that the smaller model thought that this is the cap as well, did not detect, I think, this dining table. So there's that. Cool. So that's how you run inference. Now let's talk about the training. So before I can run the training, what I need to do is I need to pull my dataset from Roboflow universe. So what I can do is I can probably do this. Just select a version number 12, because I know that's the one that I want to use, and just download it in COCO format. File is not a zip file. That's, you know, it's great. It's great. Okay, I hope it downloaded this time. Oh, okay, you know, this is what you get if you do the live coding session. Things can break. Let me just... remove the dataset that we already downloaded. Try to pull that once again. Maybe I'll just switch that to universe. This is not great, guys. This is not great. Okay, so let me just try to download the same dataset in a different way. and but I will need API key to do that, so I just, you know, just need to move it to a different screen. Stay with me, guys. Stay with me. So if I would like to download this version, I can press download dataset, continue. Let's copy this. I'm sorry, I have no idea, guys, what's happening. We didn't even started the training with the SDK because we cannot pull the data set, but oh, I'm not sure. I think it's downloading. Oh, I showed you my API key. Just for a second, but I think it's, you know, it's an out. Account settings, Roboflow, API keys. Okay, cool. Yeah, we should be fine, even though that I show you the API key, which I really tried not to do. But it doesn't matter. Okay, so I already revoked it, guys, so, you know, you won't be able to use it. Anyway, now what we'll do happens to best of us. Yeah, it's all because that download didn't work, you know, and I panicked. But it is what it is. Okay, cool. So like I said, one of the features that we get to use on this branch, as we can use TensorBoard. So let's launch it, and I will show you how to connect with it in just a second. So this is all documented in this yet unreleased branch that we have, but we'll probably release it today, and somewhere towards the bottom you'll get all the documentation, how to set up the TensorBoard, how to connect it to the training. So you can certainly take a look over there, and we will run the training. We don't need those commands that are here anymore, because we can do this. Okay, so I'm triggering the training right now. As you can see, so from the SDK, from the Roboflow SDK, I get the path to my local directory where the data set is located, and I'm just passing it as a parameter. I will train for 10 epochs because we don't have the whole day to do that. And I will use the batch size of 16, which I hope will not blow up our A100. Gradient accumulation step of 1, learning rate, and the output directory. Important thing that the output directory here needs to be the same directory that we pass to our TensorBoard, so that we'll be able to see the logs from the SDK in the TensorBoard. And first epoch, or first 2 epochs already behind us. That was fast. So let's see how it goes. If we will refresh the TensorBoard, maybe we'll already see some logs. Okay, some data is already here. We can see that the loss is going down. This is good. This is what we want to see. Let me just close the terminal. Yeah, so we see that the logging to the TensorBoard is working, and the model is training. We are already at epoch 3. Cool. So let me just yeah, hide this. Maybe we can take a look at our in-platform training in the meantime, while we wait. Let's take a look here. Yeah, so our model and platform is also training. We are at epoch 4. So I think that, you know, because we are running NVIDIA 100 in the Colab, we'll just finish that a lot faster than they do, but that doesn't matter. Okay, while we train, let me just explain also one thing. So our SDK has integrated gradient accumulation, which means that, you know, if you are using smaller GPUs, you can pretty much have exactly the same experience that I have in the A100, because you would use smaller batch size, because obviously on that smaller GPU, you don't have that much VRAM. So you wouldn't be able to train with batch size 16. But on a smaller GPU, what you can do is you can have a batch size of 4 and gradient accumulation of 4. That means that you would have kind of like you would update your weights after four learning steps. So you would process batch size of 4, batch size of 4, batch size of 4, batch size of 4, and then update gradients instead of you know, doing that each time, because then you may just as well overtrain your model. Cool. Okay, so the model is training, as you can see, fairly fast. We are already at epoch pretty much 8, yeah, because we numerate them from 0 to not from 1, but from 0. Let me just refresh that once again. Yeah, you can see that the loss is still going down nicely. And our metrics like MAP, MAR are going up. Oh, that's a good moment to talk about one more features that we have in our repo. So when you train the model, you actually train 2 models. And that's because we are, where is it? Result checkpoints. Yeah. So we are using something called EMA. So it's exponential moving average model. So we pretty much have a model that we update every epoch, like you would usually do that. But we also have a second model where we use moving average to update the weights. And that process tends to be a lot smoother, because you don't have like those bumps that happen sometimes when you train the model, where one epoch you optimize and the other epoch, because the data was slightly different than the normal distribution, you actually get worse loss. Here, because we use that moving average, you can get a better model in the end. So we actually, importantly, we actually train 2 models, even though that it looks like we train 1. Okay, our training is, I think, completed. And now what we can do is, in our output directory, we saved an image storing our metrics plot, so I can show you that. So like I said, it's only 10 epochs, guys, so there's that, but we can see our average precision. So average precision at 50 is pretty much right now going horizontally, and we are reaching around 80, and mean average precision 5095 is around 50%. Of course, typically when you would train the model, you would keep the training going for longer, but this time we just wanted to save a little bit of time, so I trained only for 10 epochs. But you can see that most of the learning is pretty much done very fast. Like I said, the model is very fast at converging. So there's that. Now we can use supervision to load the test set of our data set. You can run the inference on example images, just, you know, get a little bit of understanding of how the model is performing. You can also run it on more images. So here we are running that on 16 images, and we can see that the model, for example, consistently detects goalkeepers, which is one of the key complexities of that data set, is that we have underrepresentation of goalkeeper class in the data set, but the model consistently detects those goalkeepers. So it's already learned, you know, big chunk of what we wanted to learn. Yeah, and at the end there is like mean average precision calculation, but we already calculated that here. Okay, cool. So that's how you train the model. That's also how you run the model, because to run that those examples, I need to run the model. So I also show you that. The last thing that I probably wanted to show you is real-time stream, or whatever I will be able to do locally. Okay, so let's try to do that. Give me just a second. I need to set up stuff locally. Okay. So if everything will work as expected, then I will show you how to run RF-DETR locally. And run it through my webcam. So I think that would be pretty cool as well, because I think that many of you would run it this way. Okay, cool. So let me just clean stuff up. Cool. Okay, I have, so here's my terminal. I hope that you will see everything. I hope now it will be just a little bit easier. So one of the last things that I would like to show you is how to set up it locally and run it on a video stream. So I created a local directory. I have the app PY file over here, and what we'll do is we will create a local Python environment called VM, and we'll just source into that environment. And what we'll need to run first, maybe I will do it through the SDK. So to run it through the SDK, we will need to pip install OpenCV, supervision probably, and RF-DETR package. So for dependencies, and when it comes to the code that we would need to run to have the live stream consumed, we also have that as one of the examples in the RF-DETR repo. So here we have inference, show how to run inference with our DETR. We have inference on the video, and we have inference on the stream. So what I will do is I will just copy that. In the meantime, our dependencies are installed. At least one thing during that stream that is going well. And now what I would like to do is have a larger font somehow. Or there's also like something like presentation mode. Sorry, guys. Sorry. Nope, that's not the one. Maybe font. Sorry, guys. I know that I should... Oh, that was that easy. I didn't know how to do that. Okay, sorry. You can also do it with command and wheel. Sorry for that. Cool. Okay, so I just copied that code snippet that we had in our repo without any changes. That will use SDK, importantly. So now I will just Python up and try to run it. And that will take a little bit of time because, you know, we need to pull the weights to the model. But once we do that, I hope we'll be able to run it. Takes a little bit of time. I could have, and actually should have prepared that before the stream. But, okay. There's one more thing. We install additional dependency in the meantime. So now we pull the weights. In the meantime, question. Do you guys prefer when I'm on the green screen? Or those of you who remember how the streams looked like in the past when I was, you know, in the big rectangle, you wanted that before? Because I think that the green screen adds a little bit of that, you know, fun, but I'm still not to use that. So we can do a little bit of poll in the meantime in the comments, in the chat, if you like that change or not, while we wait for my very slow internet to pull 350 megabytes from our servers. Okay, the model weights are loaded, and that's it. That's me. On the green screen, I have phone, see, cell phone, I have the water. What else do I have over here? Not a lot of things, to be honest. Yeah. Oh, maybe cap, yeah? Cap should also be in the COCO dataset. This is the set of classes that I was talking about, yeah? So, yeah, that will be a very good screenshot from that point. Yeah, that's pretty cool. Cool. So that is real-time object detection from the webcam stream with the SDK. And now what I will try to do is real-time object detection with the Inference Package. And to do that, we will pip install in the same virtual environment, pip install inference. So like I said in the beginning, the home of the model is our RF-DETR SDK, but because we use Inference internally to run our models, and we also open source that package as a kind of like general library for computer vision inference, then we also added that model over here. And now, if we would like to run this model, we need to, I need to just take a look at the Roboflow inference docs. Just a second, guys. Yeah, so here is the docs for the inference. Let's just go RF-DETR. This is not the inference docs. This is the Roboflow docs. This is the inference docs. That's right. Sorry, guys. Sorry. Cool. Okay, so here's the code snippet to run RF-DETR. So we just do from inference import get model. So we just can remove this. Okay, doesn't matter. And then we just take a model. Just go with this. We go back over here. We replace this with this. We move model initialization over there, and those are predictions, so we need to convert them into detections. So we do that like that. Okay, cool. So now what we have is, we can just remove that. So we initialize the model, but differently. We use get model from Inference Package. Then infer, set the confidence, convert, because Inference does not return you detections in the detections format from supervision. They have their own format, but the RF-DETR SDK does. So we need to do this conversion, and then the rest of the code snippet is just like before. And now, fingers crossed, we can just run it and it will work. It'll be very cool. So there are probably weights being downloaded in the meantime. Let me just take a look in the chat. Does classifying teams and goalies with different colors and adding opacity in the label background slow down your processing during testing? Not necessarily. I mean, those are like negligible. The opacity is something that is expensive in OpenCV world, and supervision is built on top of OpenCV, but colors are not necessary. Like it's almost cheap. There was something. So you can see this is when we run it through inference. Once again, phone, once again, bottle, and this whatever that is just the rig that I use to hold my camera for the streams. And this is the cap. You see, everything works both through the SDK as well as through the inference package. Does the model somehow relate to Detectron 2? No, Detectron 2 actually is the framework that Facebook released, like in the object detection universe. That was very long time ago, and no, it's not related in in any way. Do you plan to release? By the way, if you have any questions, now is the time, because I'm slowly wrapping up the stream. So I will definitely try to respond to all of your questions, but at some point in the near future will end. That's why I'm on the full screen right now. But I want to show you one more thing. You remember, we trained that model already in the Colab, but it's still training in the app. That's the power of batch size 16 versus batch size 4 probably over here, but it's still training in the app as well. Okay, back to the full screen, and let me answer more of your questions. Do you plan to release pre-trained models for classification, segmentation, pose, OBB, and track? So we are not saying no, but there are like no immediate plans to do that. I think in many ways it will depend on the success of the Python package and the project and the model as the whole. Because if the model will be popular, then I think that there is a chance that we'll release more checkpoints for more tasks, but not in the near future. So to make it more possible, guys, I just send you the link to the repository. You just need to leave the star over there. That definitely increase the chance of us releasing checkpoints for more tasks. What a nice green screen. Thank you very much. Did you try fine-tuning in object counting data set like FCS 147? We didn't. But like I said, we fine-tune on COCO and we fine-tune on object 365. But only COCO weights are under Apache 2 license. The object 365 are available on the platform primarily for the fine-tuning. We don't plan to release them publicly, I guess. How does the model perform on small data sets? I mean, depends on what you say is small data set, but if your small data set is few hundred images, then you're probably fine. When I say fine, it will be training, still very fast, and I think it will be converging also very fast. Can it be used for reading license plates? No, it only detects stuff. It cannot read. So it's detector, not like a VLM that can do, detection and OCR and other tasks and only detect. Also, please show fast the best way to deploy the model. I think that the fastest way to deploy the model is to do it through Inference. So if I know that James, I'm not yet sure, but he was in the chat, is working on the kind of like the blog post where he will show you how to deploy RF-DETR on Jetsons through the Inference. So we will definitely have more content on like deploying the model. But I think that the best way to do that probably right now is to just upload the model to Roboflow and then run it through Inference. Have you tried, maybe have planned to check this on a Lavis or similar dataset? I think that we benchmarked on Lavis dataset internally. We just didn't release the numbers. I don't want to lie to you. So if you want to have answer to that question, which I won't be able to tell you from my head, unfortunately, I'm sending right now in the chat the invitation to our Discord, and just join the Discord, guys. And if you have questions like this that I just am not prepared to answer, then just reach out to me over there on the Discord and we can go back to this conversation. James is saying that we are working on Jetson blog post right now. We hope to have it next week. So if you would like to detect, drop that model on the edge, then we should some content for you guys next week. I see that already 2 more people joined the Discord, so that was pretty fast. I should do that every stream. I should just every stream. This is our Discord, guys. Join there. Can you make a tutorial video about traffic sign recognition YOLO on Raspberry Pi? We don't do a lot of content on Raspberry Pi because you pretty much, I think, can only run like the nano version of the YOLO, and it's very unreliable, let's call it this way, because it's so small. But I had a tutorial for road sign detection. Once again, if you will go to the Discord, because I will probably need to spend like 10 minutes to look for the link to that tutorial. So just join the Discord, reach out to me, and I will try to find the link to the road sign detection tutorial. But it won't be for the Raspberry Pi. That's the sad part. We have like 15 more people on the Discord. That's awesome, guys. Thank you very much for joining. By the way, I will let you know about the upcoming streams. I am really active lately on Discord, so you can really get me there. Crazy how I was just thinking about the show person of interest when you did the green screen scene. Yeah, exactly. Can this do segmentation? If so, no, it can't do segmentation. And like I was responding to a very similar question a few minutes ago. If the model will be successful, then there is a high chance that we'll do more tasks. If it won't get big traction, then object detection is all we'll have probably. So Chris is asking once again about the Jetson export. We'll have content about running the model on Jetson next week, so stay tuned. Join the Discord to be up to date. How is MAP small compared to other architectures such as YOLO? By MAP small, do you mean detection of small objects? So detection of small objects, I think, is one of the, I don't want to say like a weak side of the model. I would rather say that we are yet not sure. Maybe that's a better answer. But if you want to compare RF-DETR to other models, I created a Hugging Face space called YOLO Arena, which is no longer that accurate because we have RF-DETR is not YOLO based, but I created this Hugging Face space where you can test all the YOLO, like latest YOLO models and RF-DETR. So I don't know, you can just run this, yeah. And when you talk about small detections, yeah, it is a little bit, I would say. So here is RF-DETR. It's a little bit on our weaker side, especially over here. We don't detect those people that well. I can lower the confidence threshold here, but that may introduce other problems. Right now we can detect them, but probably here we have like a double detection. So I don't know. I think that you should just check. And certainly if you will fine tune on your custom data set, then it will perform like significantly better, because that's one of the things, like we say that we are COCO, SOTA on COCO, but it's not that important. What is important is that the fine tuning is really powerful. Yeah. RF-DETR compare with Qwen 2.5VL. Those are just completely different models. Yeah. So Qwen 2.5VL can do, like, it's very good at reading text. It's not like object detection wise. RF-DETR is way better object detector than Qwen 2.5VL, but 2.5VL can do like zero shot detection. Yeah. So, just completely different models with completely different set of possibilities. If you want to have zero-shot detection, then you probably go for Qwen 2.5 from those two. If you want to fine-tune your custom dataset for object detection, then you definitely go for RF-DETR. So there's that. Oh, by the way, I also have another space dedicated to RF-DETR, this one. So over here you can test RF-DETR on like images. Let's see, I was saying that we don't detect those people. We don't detect them if you use the small version of the model. If you use the large one, we easily detect them. Yeah. So you can just test that on a few different use cases. And what is cool, I also added video. So if you will upload, if you will upload your videos, then you can test on the videos as well. So just a side note, I will also paste that link in the chat in the meantime. What other questions do we have? Thank you for the stream. Great video. I mean, sorry for being late. Yeah, but I really wanted to show you that stuff that I shared on Twitter. Yeah, that we converge significantly faster. I think that's really wanted to have that on the stream. That's why I was late. Because when I tried Dyno V2 backbone, I had a bad result on small objects compared to, yeah. So we also use Dyno. That might be it. My theory is because, what is even more crazy, and I didn't have that on over here, that model runs at 640 input resolution, and that model runs at 560 input resolution. So we have a significantly smaller resized image that is passed through the neural network. And I think that we might be slightly worse at small objects because we just resize it. But you can also mitigate that problem. We allow you to set the resolution. So by default, this 560, but you can set it to larger. Of course, then it will be processing slower, but you might be better at detecting small objects. But yeah, maybe that's Dyno V2. I'm not sure. If you use USB Coral accelerator, it can increase FPS YOLO object detection on Raspberry. Guys, I have Coral in my drawer and I never used that. So I'm sorry. I'm sorry. I used NVIDIA Jetsons. I can probably, tell you something about using models on those boards, but not on Coral, unfortunately. Nice recovery. See you tomorrow, GitHub stream. Yeah, I am totally unprepared for that GitHub stream. By the way, there will be just a small advertisement, guys, okay? I got finally noticed by the GitHub team. And tomorrow there is a stream on official GitHub YouTube channel. And I will be talking about supervision because we crossed 25,000 stars and they invited me. So if you have time tomorrow at a very similar time, I think, because it will be an hour later. So pretty much, yeah, right now, tomorrow, come and say hi during the stream. I will send the link as well. By the way, do I look creepy on that image or not? I think I look kind of creepy on that image. I'm not sure. Okay, going back. Is there any nice article that examines RF-DETR model or has GitHub repo? Yeah, so James sent the link to the article. So the link to the article is in the chat. Like I said, we might release ArXiv paper. I don't want to promise that because it's not me who will write that. So I don't want to promise that I will do something or will do something when I will not do that. But there is a chance we will release ArXiv paper. But right now, the technical report that is linked in the chat is the best we can have. have you tested this with the football player detection project? Just briefly, I only tested, trained for like 10 epochs or something like this. So I think that we can get a lot better. So I can fairly say that I didn't yet have time to like test it properly on football dataset project, unfortunately. Yeah, no more questions on the chat, guys. That's great. I feel that that was awesome stream. I'm super excited about that project. I think that the community really needed like a truly open source model that is available under like Apache license with weights open source and with the code open source. So yeah, I'm really excited about that project. Like right now, it's very important for us to, you know, to get your feedback, for you to try the project, to leave, you know, ideas for the improvement, and give us bug reports if you see something not working. And generally try to use the model. And if you will do that, then I think that we might actually, you know, build it into something even bigger with like different tasks and, you know, do other stuff. But that first model is very important for us. So that's why I kind of like, you know, ask you for all of those stars on that repo, because that really helps us out. Yeah. So, you know, if you take a look at licenses of top object detectors right now, you'll see that a lot of them, it will be very hard to use in the enterprise project. Yeah. And this one trains very easy. And yeah, we'll work on deployment part in Roboflow to give you more options probably. But yeah, still, I think it's a model that you can use, and it's, you know, truly open source. So yeah, I really hope that the community will just kind of like embrace that. I can tell you it's very hard to promote object detector, real-time object detector, if it's not called YOLO. If we would call it YOLO 13, I promise you will have like 5,000 stars on GitHub right now. But because, you know, it's the detection transformer, and there is like RF-DETR, the most famous from all of them, but it's not that popular compared to YOLO. It's significantly harder to promote that project than if it would be called YOLO, but it doesn't matter. I think we are still doing a great job. So there's that. Cool. Okay. I'm wrapping this up. I hope that you had great time. We had a lot of people on the stream. We usually have like 60 people. Today, at some point, we have like 160. Thank you very much for joining. Thank you very much for like being with me today. And yeah, if you have time tomorrow, drop by and say hi on the GitHub stream that we'll have tomorrow. And in the meantime, see you on the Discord, see you on GitHub issues, and on LinkedIn and on Twitter. And yeah, that's it. Thank you very much. Bye.